Welcome back to this explainer on the ATV320 variable frequency drive. Today, we're going to completely demystify ramp profiles and acceleration control. Look, whether you are staring at a VFD for the very first time or you're a seasoned automation engineer trying to perfectly optimize a really complex machine cycle, you're in the exact right place. We're going to bridge that gap from the absolute first principles of motor control all the way down into the advanced parameter setup. By the end of this, you'll know exactly how to protect your equipment from unnecessary wear and tear. So here's our roadmap for today. We'll start with the underlying theory of ramp profiles, map out the actual parameters, do a hands-on tutorial, look at a real-world case study on hoisting, and wrap up with your key takeaways. All right, part one, the theory segment. Understanding inertia and mechanical stress. So the big question, why can't we just flip a switch and instantly slam a motor from 0 to full operating speed? Well, it all comes down to inertia. If you're newer to this, think of inertia like trying to push a heavy shopping cart that's loaded up with concrete blocks. If you just try to sprint from a dead stop, what happens? You're going to strain a muscle. Your machinery feels that exact same way. The load naturally resists any sudden change in speed. If you don't carefully control that acceleration, the mechanical stress on your system, we're talking belts, gears, shafts, can literally tear the equipment apart. Now, for the engineers tuning in, the drive actually tracks this mathematically via the inertia factor, or the SPGU parameter. It uses this exact value to calculate the precise torque required to overcome that physical inertia without overdrawing current. It's a massive amount of physical energy, and we absolutely have to manage it. And that brings us to the actual ramp profiles. On one side, you've got the standard linear ramp. Think of this like holding your foot totally steady on a car's gas pedal. It is constant, direct, straight-line acceleration. But on the other side, we have the S-ramp. The S-ramp brilliantly solves that mechanical strain problem by adding a rounding curve at the start and the stop. By tapering the acceleration, it gently takes up the slack in the mechanical linkages before applying full torque. It's so much smoother. And while it's not pictured here, there's also the U-curve profile. A U-curve is awesome because it gives you rapid, linear acceleration in the middle of the cycle, but applies heavy rounding at the very top end to prevent the machine from overshooting its target. Moving on to part two, the parameter walkthrough. Let's take all that theory and translate it into the core parameters you'll use to actually configure the drive. This is the Altivar Machine ATV320. Now, the beauty of this piece of hardware is that it handles all of those complex physics and high-level math calculations internally. Our job is just to give it the correct boundaries. For a basic setup, your foundational parameters are ACC for acceleration and DEC for deceleration. Notice that both of these come with a factory default setting of 3.0 seconds. But look at that range. It goes all the way up to 6,000 seconds. That's over an hour and a half. So if you're running a high inertia load, like a massive centrifugal fan, you might need a significantly long ramp time just to prevent the drive from tripping. And you've got hundreds or even thousands of seconds at your disposal to do it. But we don't just set the time, we define the shape of that time. Under the ramp type, or RPT parameter, you can perfectly match the mechanical load by choosing LIN for linear, S for S-ramp, U for U-ramp, or CUS for a fully customized profile. Oh, and here's a real game changer. You aren't locked into just one profile. Using the RPS, or ramp switching parameter, you can actually wire up a digital input to switch between totally different ramp times on the fly, right in the middle of a machine cycle. Now, if you do select that customized profile, you unlock the ultimate level of control. You can fine-tune the exact rounding percentages at the start and end of both your acceleration and deceleration using parameters TA1 through TA4. For instance, TA1 sets the start acceleration rounding anywhere from 0 to 100%. Tinkering with these custom rounding percentages is honestly what separates an OK setup from an absolute expert-level configuration that maximizes the lifespan of highly sensitive loads. All right, part three, the tutorial segment. Let's navigate the HMI and see how to punch these settings in. When you're looking at the display on the ATV320, here is a pro tip. Watch out for the dash. A dash after a code, like SIM dash, means you're looking at a menu folder, not an editable parameter. You've got to press enter to actually go inside that menu to find actionable stuff like ACC and DEC. Let's say you're changing your ramp type from a standard linear profile over to an S-curve for a delicate load. You'd use the arrow keys to select the digit, use the jog dial to dial in the new type, and hit Ent to confirm it. And the cool part? When you hit run, you won't just hear the difference in the motor, you'll see it on the screen. Instead of the frequency numbers just marching up linearly, you'll literally watch the acceleration start out slow, build up rapidly in the middle, and then taper off smoothly as it hits the target frequency.
While those arrow keys and that central jog dial are fantastic for your initial setup, modern automation is all about flexibility, right? During live operation, you could wire a digital input, let's say DI3, directly into the drive. When a PLC or a limit switch triggers that input, it activates that RPS ramp switching parameter we talked about and instantly changes your deceleration profile mid-cycle. Nobody ever has to physically touch the faceplate.
Okay, part 4, case study on advanced hoisting. Let's look at some real-world industrial applications where getting this wrong causes huge headaches.
So consider a massive centrifugal fan versus a vertical hoist. They behave entirely differently. If you have a high-inertia fan and it tries to decelerate too fast, the motor essentially turns into a generator. It pumps voltage back into the drive and trips it on an OVF, or overvoltage fault. To fix a tripping fan, you extend the deceleration time and add an S-curve. But for a vertical hoist, totally different rules. The manual is super explicit here. Acceleration and deceleration ramps for hoisting must be greater than 0.5 seconds. This ensures the drive doesn't pull a massive power spike, hit its current limit, and trip out while trying to move a heavy load.
The biggest difference between the fan and the hoist is that the hoist is constantly fighting gravity. So while the fan just needs a longer DEC time and an S-curve to clear that overvoltage fault, a gravity-fed hoist literally requires a physical braking resistor. It is an absolute requirement to safely burn off and dissipate all that excess electrical energy generated when you're lowering the load. And because it's a hoist, you're dealing with physical mechanical brakes. You have to perfectly coordinate the drive's electronic ramps with the physical release of those brake pads. That's where the brake release time parameter, or BRT, comes in. You use BRT to tell the drive exactly how many fractions of a second it takes for that mechanical brake to click open. If you don't sync this up, the drive tries to apply full motor torque while the physical brake is still clamped tight, which is a fast track to severe mechanical failure. Finally, part 5, key takeaways and rules for the field. Let's distill everything we've covered today.
Rule number 1, always match your ramp type, your RPT, to your specific load. Use those long S-curves to fix overvoltage trips on centrifugal fans, and use controlled ramps with a braking resistor for hoists. Rule number 2, take advantage of ramp switching, or RPS, to change profiles on the fly. And rule 3, remember your parameter boundaries. You've got up to 6,000 seconds to work with, so use that flexibility for your heavy loads.
Which brings us to the absolute most common mistake we see out in the field. So many people just leave ACC and DEC sitting right at that 3.0 second factory default for every single application. They wire it up, press start, and totally ignore the unique physical inertia of the machine they're trying to control. So I'll leave you with this to think about next time you're out on the plant floor. Are your current VFD ramp setups actually protecting your equipment? Or are they just punishing your machinery with unnecessary stress every single time you hit the start button? It might be time to dig into those parameters, dial in some S-curves, and really take control of your process. Thanks so much for hanging out with me for this explainer, and I'll catch you in the next one.